For mature platform engineering teams, having a CI/CD pipeline is a baseline expectation. Yet, despite heavy investment in automation, teams still battle late-night deployment regressions and untraceable configuration drift across their global estate. When a fix deployed in a QA environment fails to replicate in production, engineers often blame human error or inadequate testing. But the chronic need to manually cherry-pick commits is a symptom of a structural flaw in the release architecture itself. This flaw originates from conflating three independent dimensions onto a single Git branch: the version of the code, the environment where it runs, and the specific configuration values for that region. This animated diagram of a Git commit tree shows how mapping branches to environments creates a structural merge matrix. By treating an environment as a long-lived branch, every single code change is forced to navigate a complex web of inter-branch merges. Watch the path of a single hotfix as it enters the pipeline. A critical patch is successfully tested and committed directly to the QA branch. Because environments live on parallel branches, that exact same fix must now be manually cherry-picked and duplicated across the UAT branch, the Hong Kong production branch, and the US production branch. Every manual replay introduces a distinct point of failure. Over time, as environment-specific tweaks and hotfixes compound, the branches diverge. The codebase running in Hong Kong is no longer the codebase running in the US, and configuration drift becomes a constant factor. To resolve this, we apply a single foundational rule. An environment is a place you promote an artifact to, not a branch you merge code into. Until the code version, the environment, and the configuration are decoupled into distinct layers, release velocity will be limited by manual merge conflicts and the constant overhead of cherry-picking. Decoupling these dimensions starts by locking down the code version. We manage the pure business logic exclusively through Git history and a centralized artifact repository, entirely stripped of deployment context. This requires a shift to trunk-based development. The main branch becomes the sole long-lived line of code. Release branches are cut strictly on a set cadence and exist solely for short-term stabilization. This linear Git graph shows developers working on short-lived feature branches that merge back into main. The code moves forward in a single, predictable direction. When it is time to cut a release, continuous integration triggers on a specific Git tag. Crucially, the build script strips every configuration file and environment variable out. The CI process outputs a completely unconfigured geometric block. This is the immutable artifact. This block is pushed to an artifact repository and locked, never to be rebuilt. Extracting the configuration from the build phase guarantees that the exact binary QA signs off on is identical to the one that reaches global production. An unconfigured binary cannot connect to a database or resolve a market calendar on its own. Those values must be injected at runtime. We handle this by introducing the second architectural pillar, a dedicated trunk-only configuration repository. This directory tree shows how configuration state is managed. We use 3 layered tiers: global defaults, service baselines, and specific environment and regional overlays. These are layered overrides. An overlay file contains only the specific delta for that target, such as a Hong Kong database endpoint or a regional throttle limit. Everything else inherits from the tiers above. If your QA and production files are nearly identical copies, you invite drift back into the system. By storing only the differences, the configuration stays organized and auditable. For a standard infrastructure update, like migrating a production database endpoint, a team opens a single pull request strictly in this configuration repository. Notice that the source repository and the artifactory remain completely untouched. The artifact does not change. The mechanism that binds the immutable binary and the layered configuration together in the target environment is the deployment manifest. In this model, environments and regions exist strictly as declarative text files inside a deployment directory, rather than Git branches. This YAML manifest shows how promotion operates. Updating the version string is the only action required. Upon merge, a deployment engine pulls the locked artifact, wraps it in Hong Kong configuration layers, and executes it on the target server node. Promotion becomes a metadata operation. Upgrading QA, then UAT, and finally global production just means incrementing version numbers in successive manifest files. Rollbacks are equally straightforward. Instead of deciphering an emergency Git revert on source code, you revert the manifest pull request to restore the known good state. This metadata-driven approach enables precise follow-the-sun rollouts with zero rebuilds and a clear audit trail of exactly what ran, where, and when. In enterprise software, multiple features often test together. If a single feature fails at the last minute, it must be extracted without delaying the entire release. Using git revert on a merge commit to back out a feature can poison the Git history, which may cause Git to ignore those changes when you try to remerge them later. A more reliable solution is to construct throwaway integration branches. This CI diagram shows a script that dynamically merges approved feature branches into a temporary branch labeled dev1. This is a generated build artifact, not a permanent source of truth. If a feature fails QA, you drop it from the integration manifest and let automation recreate a pristine dev2 branch with only the successful features. For teams with manual human QA, the stabilization period is longer. In these cases, the fixed direction reverses. Engineers fix bugs on the release branch first to maintain a stable testing target, and then merge those fixes back into main. Whether using manual testing or automated feature bundling, disposable integration branches protect the integrity of the final release artifact. This decoupled structure provides the architectural foundation needed to move towards modern containerized infrastructure. The core components, the configuration repository, the artifact store, and the declarative manifests are infrastructure agnostic. This split screen compares two execution models dictated by the same manifest. Left, Ansible reads the manifest, pulls a tarball, and injects YAML onto a virtual machine. Right, Argo CD reads that same manifest, pulls a Docker image, and translates overlays into Kubernetes config maps. Regional go-live differences across global markets are now handled by feature flags and staggered manifest pull requests, which prevents code divergence. By managing state via manifests today, the complex move to new infrastructure focuses on the execution engine rather than a total redesign of the release process. The structural reliance on manual cherry-picking is removed by design.